Last time we talked about special relativity for the most part. Today we're going to talk about general relativity and finally apply it to the black hole situation. And also, just like last time, we started with what that type of relativity is based on, and then we talked about its results. So now we're going to talk about what general relativity is based on, and then we'll get to the results. Okay, so general relativity is also based on two things. And the first one is called the equivalency principle. Okay, so the first thing general relativity is based on is the equivalency principle. And if I just tried to put the equivalency principle into words right now, it wouldn't make a lot of sense. It's going to be easier if I just give you guys an example of the equivalency principle, and then we'll get what it's how to put it into words. Okay, so here we go. Let's figure out a situation. Okay. Oops, forgot to turn on the document cam. There we go. All right, so here we go. Here we go. Let me just make sure that this is focused. There we go. Sorry about that. Now, let's say we're on the Earth. So here's Earth. All right. And let's say we kidnap a dude. Okay? We kidnap a dude. All right? We've kidnapped him, and we have put him in a box. And that box is just sitting on the Earth. Okay? We just kidnapped a dude. We put him in the box. And that box is completely sealed, okay? Completely sealed. You can't see out the box in any way. You can't hear out the box. There's no air holes, but somehow there's enough air to breathe. I don't know. But we kidnapped him and we put him in the box. Now, okay. Number one, is this guy going to float around in this box? Yes or no? Will this guy float around in this box? Will he be able to fly in there? Yes or no? No. He definitely would not be able to. And why? Why won't he be able to just float around? What's going to keep him from floating around? Gravity, right? Yeah, gravity's going to keep him down. So because of gravity, he's going to get stuck to this side of the box, okay? And he can jump, but if he jumps, he's just going to fall right back down. And he can walk around down here. Can he walk around on this top part? No, he can't walk around on this top part because gravity points that way, right? So gravity is pointing down. And let's say that we set it up so that, let me zoom in a little bit. Let's say that when we set it up, he was originally in the dark, but when we flick the lights on, we've timed it just right so that there's a ball right in front of his face. So the first thing he sees in the box is this ball. Now, that ball, what's that ball gonna do? It's right there in the air, right in front of his face. Don't overthink this. What is that ball gonna do? It's going to fall, right? It's going to fall. It's going to come down like this, okay? And it's going to hit the ground. And if he picked it up, he could drop it and it would fall again. So everything's being pushed to the bottom of the box, okay? And if he kept dropping the ball, eventually he might be able to set up something where he can measure how fast that ball is falling. And he would see that that ball is accelerating downward at the same rate that things accelerate down on Earth, okay? And every time he jumps, he also accelerates at that rate, and they're always going to the bottom of the box. Now, where will he think his box is, okay? If we got in there, we're like, where do you think you are? Like, in this weird kidnapping situation, yeah, he's gonna say, I'm on Earth. My box is on Earth. Please let me out. I don't know what's going on. And we're like, we're doing an experiment. It's not over yet. Okay? Now, here we go. Different situation. Let's say we kidnapped this guy's twin brother. Okay? This guy, you didn't know it. This guy has a twin brother, and we also kidnapped that guy. And we put him in an identical box. Well, that's supposed to be an identical box. Here we go. We kidnapped this guy's brother, put him in an identical box. But, okay, let's pop him in there. There we go. Nice twins. This box is not on Earth, okay? This box is not on Earth. This box is in space. And it's in space way away from any planet, okay? Way away from any planet and any star and any galaxy. It's way away from everything. So that means there's no gravity in this one, okay? There we go. Oh, you guys. Now, here we go. The difference, though, is that this box was sitting still on the Earth. It was just sitting there, sitting on the ground. This box is not, because we have attached a rope to the outside that's attached to a rocket ship. That's supposed to be a rocket. We'll write that on there. There we go. Worst rocket ever. Anyway, here we go. Now remember, this is a totally sealed box, so this guy can't hear the rocket and he can't see the rocket or anything. And what this rocket is doing is it's pulling this whole box up at the exact same rate that things accelerate down on Earth. So here we have acceleration upward. So the rate that this ball accelerates down in the Earth scenario, this whole box is accelerating upward constantly, okay? At that same rate. Now, will this guy float around in this box? Or will he end up getting stuck to one of the sides? Is he going to float, or is he going to get stuck on a side? Let's see if we can figure that out. So he's not going to float. There's no gravity, so it seems like he should be able to float. But he will get stuck to a side of this box. Because this box is constantly moving, which side of the box is he going to get pressed into? The top, the bottom, the left, or the right? Which side of the box will he get stuck onto because of the movement of the box? Top, bottom, left, or right? The bottom. The bottom. He'll get stuck on the bottom. There's no gravity, so if he was not in the box, he'd be able to float around. But because the box is moving up, if he was floating right here, the box will come up and slam into his feet. So his feet are going to get pressed into the bottom of that box, okay? And if he were to jump, he would be floating up here, but the box would come up and hit his feet again. So if he floats, the box keeps hitting his feet. The box keeps hitting his feet. So it's going to look like to him that he's just jumping. Remember, he can't see outside, so he doesn't know his box is moving. It's just going to look like this. And let's say we set it up so that when the lights turned on, there was a ball in front of his face. And because there's no gravity, that ball is trying to just float in space. But because the box is coming up, it's going to look like the ball is doing what? If the ball is floating in place, but the floor is coming up, from the point of view of that guy in the box, what's it going to look like the ball is doing? It's going to look like the ball is falling. So I'll put like a little dashed line to represent what it looks like to him. What's really happening is the floor is coming up, but if you're inside the box, riding that floor, it looks like the ball is going down. And check this out, because the floor is coming up at the same rate that things fall on Earth, then that means that the ball will look like it's falling at the same rate as things on Earth. Can he, here we go, can he walk around on the top of the box in this scenario? Can this guy walk around up here on the top of the box? Yes or no? And I don't mean on top of the box like outside the box. I mean, if he were to turn with his feet up in this picture, no, he wouldn't be able to walk around up there. Because if he tried to walk around up there, that part would get torn away from his feet, right? But he will be able to walk around. It's like he's riding an elevator, okay? Now, so if this box is completely sealed, where is he going to think his box is in this situation? Where is he going to think that box is? He's going to think that box is on Earth, okay? Yes, he's going to think that box is on Earth, because if you look inside the boxes, if we ignore everything outside, what's happening inside the boxes is exactly the same. It's exactly the same. So even if we told these two twins that one of them was in Earth and one of them was in space being accelerated up, they would not be able to figure out which one of them was in which box, because these two situations are equivalent. They produce the same results, okay? And that is the equivalency principle, okay? The equivalency principle is that gravity is equivalent to an upward acceleration of your point of view. So gravity produces the same effects as accelerating your point of view upward at the same rate that things fall on Earth, in this case, in the Earth example. So the equivalency principle, again, is that gravity is equivalent to an upward acceleration of your point of view. And what we mean by equivalent there is that we mean they produce the same effects, okay? So anything that happens in this box will also be able to happen in this box.